Hello everyone, I am Pawarit Manakul from Thai Tokyo Tech ICTS program. Today I will present my AI IoT research about Bluetooth Low Energy and Convolutional Neural Network based Angle of Arrival Indoor Localization in presence of relic fading. Today I'm going to talk about the problem statement, the structure of system, and how the data process and interpret. And finally, I will talk about my idea for real-world implementation. For the problem statement, the Bluetooth Low Energy or BLE plays an important role in indoor localization and empowering the Internet of Things, such as in industrial, agriculture, and museum. And the angle of arrival localization provide low estimation error, but the approach are prone to noise, multipath, and path loss effects. The convolutional neural network based AOA we recommend to track mobile engines to improve the accuracy in varied SNR ratio, additive voice Gaussian noise, and relic fading channel. So for the angle of arrival is provided in direction finding feature in Bluetooth 5.1. The idea is using triangulation based on the direction of the incident radio frequency signal received by array of antennas such as linear antenna array or LAA. Each antenna will receive the same signal but in the different time, or in other hand we mean in different phase, that we can calculate for the angle of arrival of the incident signal. With the data more than 2 LAAs, we can locate the object. Here is the structure of system. First we begin with the transmitter, which is our object that we want to track. It will send the signal to the receiver, which is the LAA or linear array antenna, passing through the wireless channel. And then we will collect all the data and use it in the convolutional neural network to estimate the location of the object. For the transmitter or tag, we use IEEE 802.15.4 Zigbee. It used the ISM band 2.4 to 2.48 GHz frequency range. This will divide to 37 data channels and 3 advertisement channels with 2 MHz bandwidth. It has frequency hopping and uses the Gaussian frequency shift key. So for the baseband, here is the formula of the baseband. And we use the Gaussian frequency shift key modulation. It will only affect the phase of the signal. So as you can see from E and T, we can take it as the constant. And I is the modulation index, which is the value around 0.45 to 0.55 in BLE standard. The Sn has the value about +1 and -1. And here is the transmit signal formula that we get from the block code from your right hand side. The carrier frequency will be about 2.4 to 2.48 GHz. For the wireless channel, in this channel we use wireless multipath fading with AWGN and relic channel model. it will have the path loss, and the channel response formula is as you can see from this slide. You can see that in the right hand side we have the channel response here, and then we will plus with the noise. For the receiver, which is LAA, the receive signal formula is as you can see from the top formula here, and then the alpha here is the channel model, and N is the AWGN noise. So for the CNN, there are three 2D convolution layers, which each has 196 filters with 4 kernel size and the max pooling here, and we use sigmoid function. In dense layer we use linear function. So for the next topic is how data is processed and interpreted. First we have the angle of arrival measurement in 3D indoor environment, and second phase is the CNN based location estimation. From the first part, the angle of arrival measurement in a 3D indoor environment. Each antenna in array of LAA will receive the signal with different phases. As you can see from the figure here, the antenna 1 and 2 will receive the same signal with different phase. And we can calculate for the angle of incident signal from this formula. By using 4 LAA here, we can get the location, which is the x and y coordinate of the object from this formula. For the CNN based location estimation, after we get the data from the previous phase, we will transform and make it each pixel will indicate the spatial spectrum of the angle of arrival measurement. The spatial spectrum is reshaped to be an square angle image. Each angle image is then labeled by the respective ground truth position, or in this case is the LN here. And from the antenna incident, angle should be 0 to 180. And then we use CNN as function approximation to estimate the location of object from angle image captured in each time slot. We use the mean square error as the loss function. Here is the formula of the mean square error. And here is the data of training set and validation set and test set that the author of this paper used. For the idea for real-world implementation, in real world we have to deal with many variables such as the line of sight and multipath fading. As you can see in this paper, we use AWGN plus Lilik channel model to mimic the situation that there is no line of sight. In real world, there is the situation that it has the line of sight, so it has the dominant signal. For the obstacles, in real world there are many types of obstacles which has the different signal absorption index and scattering. In real-time problem, in order to provide high accuracy, the system will require more time to estimate the location of the object, and we have to concern about the real-time problem. And here is my opinion to approach the system. First, we begin with install the system in the indoor environment, such as room or the building, and then we create the building plan. And then we begin the experiment to collect the incident angle, and we collect the real world location coordinate. And then we train the CNN to estimate the location of the object. Thank you for your attention. Here is the reference.